Okay, as you can tell from the title, this video covers modular arithmetic. So I'm just gonna get started. To talk about modular arithmetic, we must first define what a modulo is. In most relevant programming languages, the modulo is an operator which returns the remainder on dividing two integers. So coming back to modular arithmetic, we can define it as arithmetic dealing with remainders. And the arithmetic operations would be addition, multiplication, subtraction, and division. Now let's look at some properties. Here we can see that a plus b, the whole modulo m, is equal to a modulo m plus b modulo m, the whole modulo m. And similarly for multiplication, we just need to replace the addition sign with the multiplication sign. But for subtraction and division, it's a bit different. Here for subtraction, we can say that a minus b whole modulo m is equal to a mod m minus b mod m plus an extra m, the whole modulo m. I will discuss this separately in a minute. And coming to division, we see that a divided by b modulo m is equal to a multiplied by the inverse of b on m whole modulo m. Again, this inverse I will discuss in a minute. Coming to subtraction, you can see that I've written 2 modulo 5 is equal to 7 modulo 5. This is because when 2 is divided by 5, we get 2 as a remainder, and similarly when we divide 7 by 5, we get 2 as a remainder here as well. Formally, this is written as 2 is congruent to 7 modulo 5. Similarly, we can extend this further. So 2 mod 5 is equal to 7 mod 5, which is also 5 plus 2 mod 5, which is also equal to 10 plus 2 mod 5, which is equal to 12 mod 5. Now, all of these remainders are equal. So let's see what happens if we extend it backward. Let's consider 2 minus 5 mod 5. We get minus 3 is congruent to 2 mod 5. But remainders must be positive. We can't have a negative remainder. It needs to be in the range 0 to m minus 1, where m is the modulo. So to fix this, we simply just add m to the negative till it becomes a positive. So here we can see that minus 3 is converted to positive by just adding 5. So now it's 2 mod 5. This is consistent with the result we got above. Moving on to division, we need to find the modular inverse of the remainder. So as I've discussed above, we need to find the inverse of b on m. So to find the modular inverse, let's go through these steps. For a given a, we need to find some value x such that a times x is congruent to 1 modulo m, which can be rewritten as x is congruent to a power minus 1 modulo m. This only exists if a and m are coprimes, or more formally, if GCD of a and m is equal to 1. So this a power 1 we can calculate with Fermat's little theorem, which states that for some prime m, for some prime modulo m, a power minus 1 is equal to a power m minus 2 modulo m. Now, there's a small problem with this. In most problems, m would be a large integer, such as 10 power 9 plus 7. And if we try to do this linearly, we'll get a TLE. So there's a technique to do this much faster. It's called binary exponentiation. In this, we take the exponent and we break it down into its binary representation or its powers of 2. So here I've done a power 11 is equal to a power 8 plus 2 plus 1, which is equal to a power 8 into a power 2 into a. So how do we calculate this? We start with a and we can get a square, which is equal to a into a. And then we can get a power 4, which is equal to a square into a square. And this a square is what we got in the previous step. Similarly, we can get a power 8, which is equal to a power 4 into a power 4. And we just plug in these values in this equation above. So this is the function in C++. It takes as parameters the base and the exponent. So a is the base and b is the exponent. We initialize the result to 1 and we use a while loop while b is greater than 0. If the last bit of b is equal to 1, or we can say if the last bit is set, we include the current power in our result. Since we need a power 8, a power 2 and a power 1, we'll be considering these for the result, but not a power 4, since we don't have a requirement for 4 here. That's what this b and 1 is checking. So we move on by squaring the current a. So like here we have a square is equal to a into a power 4 is equal to a square into a square. We take the previous value of a and square it. Then we right shift b by 1. This is to check the next bit of b in the next iteration. And then we just return. So we can plug these in now. Consider x by y modulo m. That's equal to x into y inverse modulo m, which is also equal to x into y power m minus 2 modulo m. And this value we can calculate with this function. So the last thing is, why do problems have this number? Why do we need to modulo by 10 power 9 plus 7? So this is just due to the fact that a large prime ensures that the GCD of A and M are equal to 1. And if you recall, I had mentioned that modular inverses only exist if GCD of A and M are equal to 1. So 10 power 9 plus 7 is a huge prime. So anything less than that, if we enter in, if we input into this value of A and it's less than this, the GCD will always be 1, because the only factors of 10 power 9 plus 7 are 1 and itself. And the input will usually be smaller than this. So that is why we use this huge number. Okay, so I have some snippets on how to write these in C++ code. So I've defined a const modulo m, which is 10 power 9 plus 7. This can vary across problems. So we have addition, which is a mod m plus b mod m whole mod m. And multiplication, you need to be a little careful. So we have a mod m whole into b mod m the whole modulo m. So we need these brackets here because modulo has a lower precedence than multiplication. And for subtraction, we have a mod m minus b mod m plus m whole mod m. I have covered this plus m earlier. And for division, we have this function to calculate b power m minus 2 as I discussed earlier. So make sure you have modulo m wherever you're multiplying in this function. So we have for res calculation and a square calculation, make sure you mod here. And then we just have a into bin power b comma m minus 2, which is equal to b inverse modulo m. And that's it.